Hello, everyone. I hope you can see me and hear my voice. I'm Bita, your host this evening, and on behalf of the TMLS team, I want to welcome all of you to Machine Learning in Healthcare with focus on COVID-19. We have MLOps event in the June. I will provide the link in chat section. So if you like, you can find more information and link. Please don't forget to ask your question in the chat section. Just a quick reminder, please do not click on the share audio and video because it basically is a request for being on camera, and you can still see the talk and enjoy the talk without that. And I want to introduce our first speaker. Our first speaker is Parnian Afshar. She's a PhD candidate in information system engineering at Concordia University. She's the recipient of Quebec Merit Scholarship. She's focusing on deep learning based radiomics, especially for cancer diagnosis and classification. Welcome, Parnian, and now you can start your talk.
Okay, thank you for the introduction. I'm gonna share my screen. Okay, so as Bita mentioned, I'm going to present our study on COVID-19 positive cases diagnosis from X-ray images based on Capsule Networks, which we refer to as COVID CAPS. This work is a joint study with our collaborators from University of Toronto and also Sunnybrook Hospital in Toronto. So throughout this presentation, I want to convey a few messages. First of all, is the current gold standard techniques are being successful in identifying positive COVID-19 cases? If not, what are the alternatives to these techniques? And can we use machine learning to somehow increase the accuracy of COVID-19 diagnosis? In terms of using machine learning, where are we standing right now? And what are the next steps? So the current gold standard in COVID-19 diagnosis is called reverse transcription polymerase chain reaction, or RT-PCR test. This test, however, has a few drawbacks. First of all, it has a relatively low sensitivity, which means that there's a possibility that we are going to miss some positive cases. It also requires some specific material and equipment. So there are countries that are having difficulty having access to RT-PCR kits to diagnose COVID-19 cases. And it's also relatively time consuming, which is not desirable because we want to detect coronavirus as soon as possible, and we want to isolate patients and stop spreading this disease. So alternative to this test is a medical imaging. Studies have shown that images in COVID-19 patients have some specific findings. For example, the COVID-19 infections has ground glass opacities. It tends to have rounded morphology, and they tend to have peripheral line distribution. So as you can see in these images from a hospital in Iran, from 3 different patients having COVID-19 cases, the infections are mostly ground glass and they have rounded morphology. Although the findings in X-ray and CT scans can be useful, they can have some overlaps with other viral or fungal infections or other entities such as organizing pneumonia. And this limits the ability of radiologists to accurately diagnose the COVID-19 cases. So researchers are trying to see if machine learning can increase the accuracy of diagnosis. So far, most of the studies are based on the CNN-based architectures. Um, Most of the studies either use X-ray images or CT scans. Since X-ray images are 2D, we do not have a specific pre-processing. But for the CT scans, as these scans are 3D, and we cannot afford to use hundreds of slices for each patient, researchers propose to either select abnormal slices automatically or manually and just use the abnormal slices as the input to the network, or they propose to use a patch-based input, which means that they manually or automatically detect infected regions, and they separate these regions as the input to the CNN-based architectures. But the CNN-based solutions have an important drawback, which is their inability to capture spatial relations between image instances. This means that CNNs cannot recognize the same object when it is rotated or subject to another type of transformation, even the same object that they have been trained on. So the solution to this drawback is to adopt a big data set or to apply huge data augmentation to include all possible transformations and rotations. However, as we know, COVID-19 has been identified only recently and large enough data sets are not available. Capsule networks are alternatives to CNNs that are able to capture this important spatial information using a process called routing by agreement. So capsule networks are able to be trained on smaller data sets without a huge data augmentation. And this makes them a suitable solution for the problem of COVID-19 diagnosis. And it led us to the design of our COVID CAPS framework. Our trained COVID CAPS framework is publicly available in our GitHub page, and you are more than welcome to try and test our codes, and we will appreciate your comments on our codes. I'm not going to the details of the capsule networks, but I briefly introduce the routing by agreement process, which makes the capsule networks being able to handle smaller data sets. So basically, each is a group of neurons, and this capsule represents a specific instant at a specific location, and the length of the capsule shows the probability of the instance being present. Through the routing by agreement process, what happens is that the capsules in a lower layer try to predict the output of the capsules in the higher levels through a weight matrix called Wij, which is trained through the backpropagation, just like a normal deep learning network. When the agreement is calculated between the prediction and the actual outcome by basically computing the dot product between these two vectors, and the routing coefficient is calculated in a way to give more weight to the predictions that have been more successful to predict the actual outcome. And the final output is the weighted average over all the prediction coming from the lower layer based on the coefficients calculated in routing by agreement. So we ended up with this COVID CAPS architecture. The input to our network are X-ray images from positive and negative COVID cases. All the images go through sets of convolutional layers and also pooling layers. The last convolutional layer is reshaped to form the first capsule layer. And then we have 3 capsule layers that are performing routing by agreement. And at the end, we have the final capsule layer that determines the positive and negative cases. We also modified the loss function of the capsule network to handle the class imbalance problem because we had far less positive cases in our data set compared to negative ones. So we tried to give more weight to the positive cases to handle the class imbalance problem. We also tried pre-training with an external X-ray dataset on patients having a kind of lung disease, but not coronavirus. We pre-trained all the capsule network using this external dataset, but for the pre-training, we kept all the convolutional layers fixed, and we just fine-tuned the capsule layers on the original COVID-19 dataset. We use Adam Optimizer with 100 epochs and a batch size of 16. We also use a separate validation set to see, to get the weights that are giving the best performance, and then we use these weights for testing our model. So for our experiments, we use two separate data sets. The first one is the original COVID-19 dataset, which we got from the COVID-NET paper from University of Waterloo. This dataset contains patients with 4 labels: normal, bacterial, non-COVID viral, and COVID-19 infection. We regrouped normal, bacterial, and non-COVID viral cases as negative cases and COVID-19 as positive cases. For pre-training, we used an external data set from a paper published in CVPR. This data set contains almost 15 findings related to lungs, but to have fewer classes, we regrouped these findings as no finding, tumors, pleural disease, lung infection, and others. So in this way, in the pre-training phase, we have 5 classes in the final capsule layers. And when we want to fine-tune using the COVID-19 dataset, we remove the last capsule layer. We insert 2 capsules to represent positive and negative COVID-19 cases. As you can see in this table, our pre-trained COVID caps reach an accuracy of 98%, sensitivity of 80%, and specificity of 98%. Our sensitivity is lower than other reference by Sethi and Behera, which use the same data set and binarize the labels as we did. However, I would like to mention that this reference has 23 million trainable parameters, whereas our proposed COVID caps has only 295,000 trainable parameters, which means that we can train the COVID caps in a more timely fashion, and we need less powerful computational resources. And also, as you can see in the ROC plots, the pre-trained COVID caps has a higher area under the curve compared to the COVID caps that is not pre-trained. We also investigated the false positives from the COVID caps to see which kinds of labels are more likely to be confused with COVID cases. And we observed that 54 of the false positives are just normal cases, whereas only 27% and 90% of the false positives are related to bacterial and non-COVID viral cases. We are continuously improving our COVID caps architecture as new data sets become available. We are also trying to collect a rich city data set for COVID-19 to replace and transfer the COVID caps to a city-based network instead of X-ray. And we also want to try to combine different modalities to see if different modalities can capture more detailed information and contribute to a higher accuracy. We also want to consider RNA results and clinical factors to improve the performance. Thank you for your attention. I think I should get questions now.
We have a few questions, and
Okay.
I will ask them on behalf of the participant. One is that how did were images of pneumonia handled?
Okay, so the input to our COVID caps are X-ray images, which are 2D images. We didn't have a specific pre-processing to have a smaller number of images. So the input is just the raw image, which we downsampled for the sake of complexity.
Okay, thank you. I hope you get your answers. If not, please post again your questions and she can explain. And another question is, if you calculated the F1 score, what is the F1 score?
No, we did not calculate the F1 score, but our code is available in our GitHub page. I can help this person to calculate the F1 score.
Amazing, thank you. Thank you so much. So let me see if we have another question. We have another question that said, since patients with COVID can have normal CTs, do you think any AI system for medical imaging can replace a direct viral test? If not, then what is the value of developing these systems?
So yes, a challenge in using CT scans is that a lot of slices will be healthy and a few of them will be infected. So what people are doing currently is just to manually select the ones that seem abnormal and feed the abnormal ones to the network as candidates for COVID-19. They may not be actually COVID-19, but they are the input to the network to see if they are or not.
Okay, and another question is that what are the next steps in your attempts to combat COVID caps? Sorry.
So first, we are trying to collect CT scans to change our capsule network to a one trained on CTs, not X-ray images, because CT scans can catch higher details for this disease. And we also want to combine X-rays and CT scans to see if this can increase the performance.
Okay. And another question is that, have you tried this architecture for any other clinical groups like cancer or anything else?
Yes, we have actually quite a few publications on using capsule networks for lung tumor and also brain tumor. For this specific disease, we try to use the validation set to get the best architecture. So the architecture is a little bit different from the previous ones, but the capsule network is basically the same.
Thank you. Thank you so much. And one of our participants asked, could you please share the GitHub page if you can?
Sure, I can share it, I think, in the chats area.
Yes, you can. You can share it there, or you can send it to me, and I can, if you can see the chat section, I can provide the link for our participant to see.
I just copied the link. There it is.
Amazing. Yeah. Thank you so much.
You're welcome.
So everyone, if you have any other question, please don't hesitate to ask. And Parnian shared the GitHub link to their work, so you can check their work and see and connect to her for further questions. Thank you so much, Parnian. It seems that
you're well welcome.
They don't have any questions. Thank you so much for your talk and for your time. And please enjoy the other talks. Thank you so much.
Thank you. You too. Bye.
Bye. So everyone, you can enjoy another talks, and also you can enjoy networking session. Please don't forget that we have another event in June, MLOps, and I can post the link to the our event in June, and if you like, you can find more information about that. Thank you.